yeah, the probability we're going to get completely out of cache is very small. And the cache logic is better too. And you need unrealistically high texture resolutions to actually see a big difference there. And yeah, the techniques I discussed are still relevant, especially storing your data in multiple resolutions can often bring you a huge boost because, yeah, you're avoiding skipping through your data structures in wide steps, and a cache-friendly traversal order, accessing your data in the right order, doing it the right way, can make a lot of difference. For example, also when you store trees, you can reorder trees in a way that makes cache misses a lot more probable, and this obviously helps. So next topic I'm going to talk about is something completely different in a way, but still related to memory optimization. The point is, suppose you're coding some morphing and pulsating object, whatever, some, techno blob, however you prefer to call it. And whatever 3D API you prefer, you use a dynamic vertex buffer or dynamic vertex buffer object if you're using OpenGL, if you care for performance. And that vertex buffer will usually be in AGP memory. And well, what does this mean? First this object will change every frame, and AGP memory is memory that can be accessed both by the CPU and the graphics card simultaneously, which isn't the case for your main memory. And you need to make sure that you access this memory efficiently. And your code will look something like this, for example. You just loop through those vertices, calculate, for example, position, normal, and UV coordinates with your magic formula. We don't care about how that's done here. And no matter how you do it, you'll always store this data, plus probably some other data, depends on how your format is, in your vertex buffer. And for example, if you don't change your UV coordinates, you may want to skip writing them. Well, because what's the point in writing data? You're not changing every frame. Well, it turns out that this is a very bad idea. I already hinted at this because, well, what did I say about cache lines? They're loaded from memory on the first access, or something along those lines. Well, when I said that, I actually lied, because there are different types of memory. And a very important type of memory is so-called write-combined memory. For example, AGP memory, video memory is usually tagged as write-combined. Write-combined means that the processor, as the name suggests, always tries to combine several writes into one big write, which can be done faster, because, it's less work for the chipset and for the memory. And in write-combined memory, reads are not being cached at all, so you don't get any read caching in this case. But writes, adjacent writes that are next to each other, are combined so that when possible, whole cache lines get written. As I said, this is much faster than just storing a few double words, a few bits here and there, because it's a lot less overhead in terms of management. And this only works if you don't leave holes, because if the processor is not able to fill the cache lines completely, then you can't store complete cache lines, obviously. And so you shouldn't skip any bytes at all when writing to AGP memory. And in cases with some earlier processors, this is usually fixed on current chips, but with earlier processors, you even have to take care you write them in the correct order. This is being fixed in the current revisions, but if you have some cases of where things are slower than you think they should be on, say, a Pentium 3 or whatever, should check if they are not being written in the right order. You have to check this in the assembly generated by the compiler, actually. So this is not something you usually want to do, but this can make a big performance difference, about a factor of 4 and more. So you really want to check out that write combining is being used properly, because combined writes are really a lot faster than partial writes. So much about AGP writes. Next topic I'm going to talk about is, again related to memory optimization, is simplified memory management, which is, well, I'm going to discuss a very easy case here. In, say, a 3D engine, there's a lot of dynamic data. you build up and throw away during the course of each frame. For example, stuff like the list of visible objects, the list of active lights, instance animation data, all stuff, management information relating to it. And that's all stuff you build up during the course of each frame and then throw away afterwards. And most of this is relatively small structures. Say, well, a few integers, maybe a pointer, maybe a transform matrix. So usually stuff on the range of, say, 32 to 80 bytes. And you have thousands of relatively small allocations per frame. And standard allocators, like your C++ standard library new, isn't very good with very small allocations, lots of them. So you want to look for something better. Because, well, a standard allocator is first relatively slow compared to what you can get with optimized variants to allocate small blocks of memories. It's not particularly memory efficient for small objects. Because, when you allocate some memory, the memory manager needs some bit of information before that block, the memory block returned, so it can find where other free blocks in the memory are. There's some management overhead. That's typically around 12 bytes for usual allocators. So if you allocate structures of, say, 16 bytes, you have an additional 12 bytes of overhead for each item you allocate, because the allocator needs management information. So you have almost double the amount of data you actually allocate. And also, those memory allocators usually try to fill holes in memory to make things fit nicely. And this means, wherever there are holes, this will be filled in, and the things you allocate over a frame will be spread over a relatively big region of memory, which is not that nice for the cache. And the question is if we can do any better than that. And I wouldn't be talking about it if we couldn't. And just allocate, for example, 200 kilobytes. This depends on how much data you need and also on the structure of your engine. You can also change this value. It's not really important. And then you manage it yourself. And, how do we manage it efficiently? And, we could do all fancy kinds of stuff. We could basically write our own memory allocation routines with that. But that complexity is exactly what we're trying to avoid. So we'll try something as simple as possible. And probably the simplest possible memory allocation strategy is just using it as a stack, just assigning addresses as you go, and not allowing any free operations at all. The bare bones version of that actually fits onto one slide. This is this class, I call it the memstack class, and you just have some buffer and the current allocation pointer inside that buffer. And you initialize that stack with your size and just allocate the buffer to have that size and set your current allocation pointer at the start of the buffer. And similarly, when deleting, you delete the buffer and that's it. And there's a function called reset, which just sets the current allocation pointer back to the beginning of the buffer, and a function called alloc, which corresponds to malloc in the C library, just takes an amount of bytes, returns whatever is your current allocation pointer, and then advances that by the size of the block you allocate. So the next allocation gets memory after that. That's all there is to it. And in practice, you'll also want a type-safe alloc template. So don't have to worry about those sizes and typecasting, which is really annoying. In C++, you can do this nicely, so why not do it? And what's good about this? First of all, and most importantly probably, memory management doesn't get any shorter than that. And it can't get any faster or simpler either.